Dijkstra.
Good morning, everybody.
Class.
And the class steadily dwindles. My wife thought that it would be kind of funny if, as the last question of the exam, the question was, what room were the lectures in?
I wouldn't remember.
Yeah,
we don't know the number.
That one.
Dr. Moore, to be honest, no one knows
You
the
can
numbers.
pick it out of a list of multiple choice, though.
Yeah.
Yeah.
I don't think I still wouldn't know.
Hmm?
I still wouldn't know because it's like I memorized them by pathways now. It's like I just know where to go. I don't know numbers.
So what you're saying is, in your brain, you're running a shortest path algorithm.
Basically.
Yeah, there we go. Yeah, I would probably get in even more trouble than I already am if I pulled something like that, even if I made it a bonus question. But yeah.
Just give us 10 marks each and we
10 marks. Yeah, well. Yeah, I gotta earn those marks in my class. I don't give you marks for friggin' math journals. Jeez. I have like a beef with math journals. Today is going to be like a very, very kind of go with the flow kind of lecture today, because not only is this like my last lecture for this class, this is actually my third last lecture at this institution, because I am gonzo. I got full-time permanent at Mohawk College, and after this I'm disappearing. I'm doing the Homer into the hedge thing.
We're never seeing you ever again then?
Probably not.
That's a rip.
Yeah.
Escalated.
I mean, some of you are probably thrilled, but yeah, it's
That's honestly.
yeah. There was like a small possibility that they were going to give me 2 FA3 next semester, because apparently only 2 people applied to teach that course next semester. I was one of them, and you know.
Who was the other one?
Oh, I don't know, but there was a preference among the people that make such decisions to reassign me from 1XC3 onto that course, because there was a slightly stronger other person who applied to 1XC3 as opposed to 2FA3. So have fun with that course.
Who's going to be the hard course?
I mean, hard or easy, I don't know if it's going to be hard or easy, because like sometimes you get a bad prof and that just makes the course really easy because they know nothing about the subject, But not that I'm saying this person's a bad prof or anything, because to say anything bad about another professor is against my code of ethics, actually. Yeah, I just, fair warning about 2FA3 next semester. It's going to be a sessional, so.
Is it worse than history or better than history?
You guys don't take COMPSCI 2FA3?
It's COMPSCI or is it software?
That's a good question. Maybe I'm talking to the wrong people.
If it's
It's discrete math.
Yeah.
Software.
For software engine? Oh, you guys don't have to worry then.
oh,
Yeah.
we're already suffering already.
Okay, all right, never mind then.
Please,
never
no
mind.
more. No
All right,
more
so it's
suffering.
the software engineers who are going to get screwed then. Don't worry about it. Yeah. Cool. So, at this point, I don't know, we've kind of already done a run-through of Dijkstra's algorithm. I'm only sufficiently ambitious to like do another example of it on the board, maybe a slightly larger, more complicated example, because that's sort of, at this point, more valuable than getting into the theorems and the proofs and that kind of stuff. But I kind of feel like the time might be better spent you guys asking me questions and maybe just doing a review session, possibly instead. But if the review doesn't go long enough, then we can get back into Dijkstra and do one more example. Excuse me, of him before we break for the winter break, as it were. So yeah. So any questions? Nobody has any questions about the exam? Have I already answered all questions about the exam? Yes.
I'm just wondering, will you
we still be having office hour like today, tomorrow?
Today I'm not going to be here this afternoon. Tomorrow I'll be in my office, so if you wanna grab me tomorrow, then that would be possible. Friday I'm not going to be on campus because I'm not teaching any classes, and my wife is like, listen, if we don't address the Christmas problem, the Christmas present situation, then we're going to end up doing it Christmas Eve, and that's not good. So, yes.
Isn't that a Black Friday problem where you get all the Christmas presents then because you save money?
Oh, I mean, you should, right? It makes a lot of sense to shop on Black Friday.
Well, that weekend specifically, because like even with Amazon, even if you don't like Amazon, you can still order stuff there for these sales.
Hey, listen, man, like, I just work here, you know?
Mm-hmm.
All I know is the Christmas presents need to be bought, and they haven't been bought yet. And yes, we're going to be paying money, but you know, that's life. So any questions related to course content at all? Anything you want me to go over?
Just in general, for like when we were talking about like the OM stuff, just like there was one question I just wanted to go over because like it was for like deletion and stuff. So like, do we only look at actually deleting the value, or do we have to look at like how we find the value and then delete it?
Deleting over what data structure?
Linked list.
So the way that deletion on linked lists is defined in the slides is that you already have a pointer to the node that you're deleting.
Oh, okay, never.
So
that makes more sense now.
So basically, that's like that's principle of encapsulation, right? You have a find operation and you have a delete operation that are separate operations, so that the find code can be reused for, you know, instances where you're trying to find but you're not trying to delete.
Yeah.
Right? Now in arrays, it's like find is trivial, right? Because it's just item lookup. It's just, you know, index lookup, array offset calculation, etc., etc. But in linked lists, no, it's the deletion operation separates itself out from the searched for the item to be deleted.
Yeah, and
although that's a lot of the time that's bundled together.
No, but like we don't have to account for the whole searching part of it. We only have to look at the deletion part, if that makes sense.
Yes.
Okay, and also just to ask, do we have to know anything about B trees? Cause like
you should know what one is.
Yeah, like know what it is, but like do we have to like be able to construct one?
No, don't worry about that.
Because like
you should know how they work and conceptually, like how they're structured.
Yeah.
But like I'm not gonna like give you a bunch of values and expect you to construct a B tree.
Yeah, and also like something similar for like the toothy trees and the red black trees. Will they be really extensive on the exam? Like, will we have to create like one of the ones on the assignments? Like that?
No.
Will it only be like 5 or 6 elements?
Let me put it to you this way. All of the multiple choice questions on the exam are worth 1 point.
Yeah.
So I have tried to like obviously some will take longer than others.
Yeah.
But in general, I've tried to design the exam such that every single question should take you no more than, 5 minutes.
Because like, you said like there's like 50 to 60 questions, I'm assuming?
Yeah, between 50 and 60 questions.
And then this is like 2.5 hours?
Yeah.
Okay.
So,
because like if given like 60 questions, which is the worst case scenario, it would be like 2.5 minutes per question, if I'm not mistaken. Am I just mapping this? Yeah.
2.5. No, that's correct.
Yeah, 2.5
2.5 minutes.
First I was doing my math, like So like.
Yeah. So, but there are questions of varying difficulty on the test. There are some true/false questions which you don't have to think as long about. So I'd say like 2.5 minutes on average per question isn't outside the realm of possibility for the test. Are some people not going to finish the test?
Yeah.
Probably. Are those people in the room right now? Probably not.
Yeah, and also just 2 more things, because like last time we were talking about this. Recurrence relations will not be on the exam. That is out.
No, I'm not. I think we've tread that territory sufficiently well.
Yeah, it's been a mess.
Yeah.
I think because like the textbook goes a lot more in depth with it, so like maybe.
Yeah, I was lied to by the slides. It's part of the problem. Yeah.
Oh, okay. And also, will union stuff be on it? Unions.
Union find? Yeah, there's like a couple questions on union find.
Oh, okay. And like, will it be like the weird wording where it's like union, like the weird like
I
five-word thing?
can't really tell you if there's weird wording on the exam.
'Cause
I
it-
don't, no wording that I produce is weird wording to me, or else I wouldn't put it on the
No,
exam.
because like the one on the midterm, it was like union fine, union, a quick union or something.
Oh, no, yeah, you need to know the difference between a quick union and a quick find.
No, that I know, but I mean like
Yeah.
like there was like it was like union fine, a quick union or something, and it was just like this weird
Yeah.
thing.
That's like sub-algorithm algorithm,
Oh, okay.
right? Union find just means
Mhm.
that it does union find, it satisfies the API.
Yeah.
Quick union means it's a subvariant of union find, so it's not like it's a different thing,
They're
right?
they're technically two different branching things from this main algorithm, I'm assuming.
Well, there are like, we studied like 4, arguably 5 different approaches to union find.
Yeah.
Each one has a different name, and rather than just, rather than just say the sub-algorithm name, I thought it was useful, to say this is union find,
Oh, okay. Yeah.
right?
Makes
Rather
sense.
than just say do a quick find.
Yeah. Good.
It's like, what is quick find? Oh, it's a subvariant of union find.
Yeah,
I was
yeah.
trying to help.
Yeah, because like I was looking at that for a good 10 minutes. I'm just like, wait, what is this again?
Would you be able to go over like a red black tree insertion? Because on the assignment, like just a few of us all got it wrong, so I'm just wondering what if my interpretation of insertion on a red black tree is incorrect.
The autograder might be broken actually.
Like all my trees are wrong.
Only my red black.
Yeah.
We all have, so the ones people who have the same trees, we have the same answers, but we all have it wrong.
Mm-hmm.
And
Well-
so I'm questioning my sanity right now.
Yeah, the red black tree answers for mine didn't it did not have like the correct number, and some of them values are not even
So
correct.
Yeah.
weird.
At some point, but you guys did manage to like follow the like naming,
Yeah, we
like
did.
the tree
Yeah.
convention. That wasn't
Yeah,
the
that
problem?
was not the problem.
Okay.
It's like the numbers are totally different, like completely
Yeah.
different. It's like our logic is either completely off.
Are they the same numbers as were given in the
yeah.
question?
Sometimes they won't be the same numbers, and other
Well,
times,
in that
like,
case, then obviously
Yeah,
it's
and
like
other
it's
times
the
it-
solution to the wrong question.
Yeah,
Yeah.
and other times it would be like the tree would be missing entire levels. It will have like the first 3, and then the last 3, not like the last 3 levels. Those numbers just don't exist, and that's when marked it wrong. 'Cause
What?
It's like
Wait, what?
yeah,
There's not enough
there's
numbers.
less values.
The answers
than
are
what
not
was
enough.
given.
The answers
Oh.
are like 10 numbers, whereas like whereas we were given like 16.
Like, yeah.
I will review these questions because like this doesn't sound like you'll forgive me. I didn't input it to the system like that.
Yeah, but
You know?
a lot of people are like reporting that. Like, we were gonna email you about it, but
I
it was like
see.
a lot of kids were reporting the autograder just completely like messed up. It was, it would either give you the wrong numbers. It would be like, oh, your answer should have been this, and those weren't even the numbers given. The tree would just be missing entire levels. It would be like marked it wrong. Be like, oh, the first 3 levels were fine, but you shouldn't even have the last 3, even though it's like okay, but where do those numbers go? Because the answer doesn't even have those numbers. So there are more numbers than what the answer is showing. If that makes sense.
Well, I understand your description. It doesn't make sense why the auto grader system would do this. Clearly this is going to need some hammering out, so I apologize for yet more issues related to the marking in this course. It's not even a matter of like the assignment was put together somewhat hastily. Like what you're describing as the solutions that the auto grader are telling you are the solutions to these problems are not what I input as the solutions to these problems. So this is somewhere something has become messed up in the system. So this is going to have to be fixed. When it's going to be fixed, I don't know. I'm still working on getting my exams together, you know. So, you know,
Yeah, can we still just do one just to make sure that
Yeah, shall we do a small one?
Yeah.
we have
Yeah, okay.
logic?
Yeah, and just out of curiosity, would it be smart just like to make a 2-3 tree and then convert it to a red black tree?
Not quite, because you have to keep in mind the left-leaning property, right?
Oh.
When you convert from a 2-3 tree, doesn't it go to the left?
Yeah, you can convert them to a left
But if
leaning.
you do a regular red black tree with not left leaning, then it doesn't
Yeah, that might be the,
relate to the 2-3 tree.
yeah, that might be the, how do you want to put it? The big brain solution is to just do it as a 2-3 tree and then convert it to a red black tree. But
Cause like I do not understand.
let's do a relatively small one. Let's do like 6 or 7 numbers.
420.
Give me a number between 1 and 100. Go.
69.
Give me another number between 1 and 100, please.
68.
Eh?
77.
77.
Trying to be funny on the last one.
Next.
23.
23.
5.
5.
47.
47.
68.
68. And 1. Okay, that'll do. All right. So 77. Right? Obviously. 23. Okay. How do you want me, I guess when I was doing it in my notebook, I did like squiggles for red links and then straight lines for black links, so I guess I'll just do that on the board. So, let's see, 23, 23, good, that's left leaning, so we're good. Then we have 5, boom, boom, boom. 5, right? So we need to do a rotation, right? So in addition to the rotation, I'm in the same step, converting the 2 red links to black links. So there we go. 47. So we go down, down. 47. Go. 68. Down, down, down. 68. Oh, by the way, that still satisfies the left-leaning property. This, we're going to have to do some rotations, right? So, rotate. It's kind of easier to just erase it. Do you mind if I... Okay. So, the first rotation we want to do is to rotate like that. So we have 68, 47, COMPSCI. Next, we want to rotate these 2 guys to rotate 68 into this position, right? So like that. And at this point, I am just going to do another one. 23, 5, 68. 77 and 47, and this link becomes red, but of course that's right leaning, so we need to rotate it again to make it left leaning, right? So we detach this guy, attach it here, and 68, 77, 23, 47, 5. Everybody simpatico on this so far? Next we've got 1. That's simple enough. Yeah. Is that a sufficient explanation, or should I do some more numbers? We good? Yes.
If we want to solve this question and it needs to have less leaning tree property, is it fine to solve it exactly like a 2-3 as a 2-3 tree, or there's going to be some different answer?
Well, in theory, all 2-3 trees are immediately and directly convertible to red-black trees. So in theory, yeah, you could do it as a 2-3 tree and then just make the links, do the links correctly. Yeah, like 2-3 trees are a bit more intuitive the way they work, aren't they? Not so much of this rotation nonsense, but yeah, it's if that's how you want to get there, then I think that's fine. I'm you know, the only hesitancy in my brain is, although the slides and the textbook both say that 2-3 trees and red-black trees are exactly equivalent to each other, like, I've been lied to before, you know, and one of the things that they do to you when you're a PhD student is they hammer out of you, never make a definite claim that you're not sure about. So, you know, if you want to, you know, take the textbook as authority, then 2-3 trees are equivalent. So, right? Cool. Any other questions? Yes.
I have a question, but it's regarding the exam more than the course content.
Sure.
So are we allowed calculators?
Yeah, you can use a calculator. You're also allowed a crib sheet, same as the midterm. Which, you know, that's being pretty generous, allowing a crib sheet on a multiple choice exam. My God. You guys should have no trouble at all with the exam.
It's multiple choice.
Yeah. No, you don't like multiple choice?
I have had high school things with like 100+ multiple choice and do them in an hour,
Oh.
along with like 20 short answer questions. And this was for like an elective. This wasn't even for like a math course or something. It was like for this weird elective that I took, because like we had to do something called a group 1 credit. So like this was one of the only courses I could take group 1.
I feel like you're going down a rabbit hole,
Yeah.
and we need to like
Yeah.
continue to focus on the class. But I appreciate high school sucks. Yes. Oh, yes, you.
Even though the exam is cumulative, how much emphasis is on after midterm stuff versus before midterm stuff?
Well, it ended up being about 50-50 split, actually. Oddly enough. Basically, my methodology for composing the exam was to go through each of the slide sets in order, and like whenever I hit something that I was like, oh, that could be a question, then I made a question on it, basically. So one piece of advice, definitely understand depth and breadth first searches. Yes?
Related question, when is your office hours tomorrow?
I'll be in my office anytime after 10:30 or 10:45. My class ends at 10:30, so yeah. Yes.
I didn't ask about this, but like when you draw graphs, when do you have to do the connection to itself?
Show me what you mean.
No,
like do it on the board. Here.
Oh no.
Yeah, do it.
Like, I probably am just like stupid. Like, so for example, if I have like a graph like 0, 1, there's like some connection thing, right? It goes like something like this. When do I do the connection to itself?
That's it. Okay, so the question is, when do we have to worry about graphs with self edges, right? So if you remember the definitions that we gave of graphs, particularly undirected graphs, right at the beginning when we started talking about graph theory, we actually disallowed self edges, right? So self edges aren't allowed in graphs as we've been studying them so far.
Yeah.
Yeah. It's kind of pointless, especially if it's not a weighted graph, because like we consider nodes to be connected to themselves anyways,
Yeah.
right? So, you know, they're kind of pointless. That being said, they do have occasional applications, particularly in the union find algorithm. That's how you tell where the root of the tree is. And if you're coming up with like a similar representation, like assuming each node can only connect to one other node, an array is actually a decent implementation of a acyclic, directed acyclic graph, and having a node point to itself, indicating the root node, is a decent way of going about showing that, right? However, when we're talking about like general graphs where we have the adjacency matrix, self edges aren't really a thing.
Oh, okay, so just only for union, for like quick find and that's it.
Yeah.
Makes sense.
Also, like if you wanted to take, for example, Dijkstra's algorithm, you know how we keep that that matrix of edges, or the array of edges. Each node has an edge to the edge that points to it in the shortest path, right?
Yeah.
You could do the same kind of representation using an array and self loops to indicate roots, or the root, or unprocessed elements, or stuff like that. But in general, no, you don't have to worry about you don't have to worry about the applications of self edges inside of like depth first search or something like that.
Makes sense.
Make sense? And besides, even if you did, it's like in depth first search. If you have a node which is a self edge, then you can't travel to it again via depth first search because it will already be marked by the first time you move there, right? So, yeah.
Because like on the slides they just didn't have that, and I just basically referenced that for like the midterm, and I was like, I got dock marks for not doing the self edge. Actually, I got no marks for that question because my original question was wrong. However, the graph thing was right. Just no self edge. I was just like confused about that because everyone got the self edge problem, where like a lot of people just didn't do the edge.
The root. Yeah. And you lost all marks on that question?
Because I screwed up the previous question. However, like, long story short, turns out I actually did the normal question, the graph question properly, which is kind of funny.
Well,
yeah.
The midterm is the midterm. I'm sure we'd all want to put the midterm behind us. So, any other questions related to course content? You're good with Kruskal and Prim? Everybody's cool on those? Yes?
Could you go over the time complexity of Kruskal's algorithm under the union find data structure?
Okay. So recalling Kruskal's algorithm, right? The number of edges that we actually have to process is one less than the number of vertices, right? Because that's like to add any more edges would mean that you would be introducing cycles into the minimum spanning tree, which would mean that it's no longer a tree, right? So in that sense, the number of times you have to iterate adding an edge to the graph is proportional to the number of vertices, right? However, Kruskal's algorithm requires the edges to be ordered by weight, right? So in addition, so we have to do that up front, right? So in essence, you know, we have a sorting problem which then proceeds into Kruskal itself. I might be introducing more letters than actually exist in that name. It's okay. So Kruskal, proportional to the cardinality of the set of vertices, right? the sorting process, what's the time complexity of one of our better sorting algorithms?
N log n.
N log n, where n is,
Size of the array.
well, in this case,
It'd be the number of edges.
yes. Cardinality of the set of edges,
Right.
yes. So, sort is E log E. Right? So, when you have two time complexities, one after the other, which one do you take? Like, what happens? How do you calculate this into one big O?
You take the bigger one.
You take the bigger one. Yes. Which of the two of these is bigger?
E log E.
Correct. Sort of never mind the fact that in your typical graph, the number of edges is going to be larger than the number of vertices, right? Basically, in order for the number of edges to be less than the number of vertices in a connected graph, the only edges that would exist in that graph would have to be elements of a spanning tree. Right? So if your graph is in any way more complex than a spanning tree, E is going to be larger than V anyways, right? Not to mention, we've got E times log E, which is going to be larger than linear at any rate, right? Linearithmic is greater than linear. So, so there we go. Does that make sense?
Could you also explain the time complexity under the depth first search? Because I was having a little bit of trouble, the E times V, the cardinality of the set of vertices times the cardinality of the set of edges.
Sure. So let me just, I think I could do that one, Cole. So the depth first search, right? Number one, every vertex is examined, right? Number two, every edge adjacent to every vertex is examined. Examination, just because your examination of an edge does not result in a further recursive call because you found an unmarked node down that edge, that doesn't mean that the examination itself doesn't take time, right? It's kind of like, in sorting algorithms, we talk about the number of compares, according to the slides, and comparisons in the King's English. The number of comparisons that you're making will tell you how, what the proportionality should be, rather than the number of times you have to do something about it, right? So, because for every vertex, every adjacent edge is examined, we have the number of edges multiplied by the number of vertices. I think. Let me think about that. Because wouldn't, okay. Maybe I'm, let me just check to make sure I'm not spouting nonsense here. Let me see if my understanding is correct. My description of the depth first search is correct. Let me just make sure that I'm getting the, oh, I'm sorry, it's V plus E, not V times E. Yeah, which is what I meant. I said multiplication, but I meant addition. Because it's like you have to examine every vertex and you have to examine every edge. You don't have to examine every edge once for every vertex. So it's not multiplication, it's addition. I apologize. Question?
That's for depth first search when we're doing regular depth first search.
actually.
Okay.
The regular depth first search is that.
So regular depth first search is V plus E. So let's take a look at the slides examining Kruskal's algorithm. Is this the correct? All right. Is this the slide you're referring to?
Yeah.
Yeah, okay. I forgot an element of Kruskal's algorithm. I forgot the cycle checking. So forgive me for this error, class. So one element of Kruskal's algorithm, which I forgot, was that you also have to check to see if the edge that you're adding creates a cycle, right? Because if you're creating a cycle, then it's not a minimum spanning tree, right? So in order to check to see if you're creating a cycle, right? The naive solution is to use depth first search to do cycle checking, right? Depth first search will of course be V plus E, right? However, you need to do it once for every edge that you add, right? So if you're using depth first search for this, then you have V plus E multiplied by something proportional to V, right? But cycle checking is actually, it can be solved more efficiently than via depth first search. Yes?
Isn't it E times V plus E?
No, recall that the number of edges that we have to process under Kruskal is proportional to the number of vertices. Yeah. So depth first search is one way to determine whether or not things have cycles. However, under union find, the connectedness check in union find between two vertices will tell you if connecting those two vertices will create a cycle, assuming that it's not currently in the graph, which since we go through the edges in Kruskal one at a time, we never re-examine an edge, right? So if you're keeping a parallel union find data structure at the same time, then the amount of time that it would take you to, like, what's your like, union find can get quite good if you use like path compression, but what's our proportionality with like, just say regular quick find?
Well, if you're checking for connectedness, wouldn't it be like nearly constant?
No, because you have to follow the tree back to the root and check to see if the roots are the same, right? So you have to get through the root, get through that tree. So, you know, in general, we're kind of like, it's kind of logarithmic.
Right, yeah.
Right? So so the find operation in union find, quick find, is logarithmic. Connected is just two find operations. So we can actually, you know, we can do this proportionally, in fact, to log V, assuming we're spending the memory on keeping track of an array for each vertex, which, you know, is like, union find is very simple. Adding it to another algorithm is like piece of cake, right? It's like you could practically repurpose the marked array for it, right? Just keep something of it with Booleans. Yes?
So can you expand a little bit about cycle check using DFS?
Right, yes. So, yeah, cycle check during using depth first search. So basically, this is the way it works, right? Let's say you've got a very simple graph, right? And then maybe 4 off here. Let's start at 3, right? Under depth first search, I'm not going to do the adjacency array, we'll just do it. So in addition to the marked array, right, which sort of you set it once and then you leave it that way for the rest of the algorithm, right? You never unmark a node. We also keep a on-stack array, which serves a similar purpose. But all that's doing is telling us whether the node that we're currently processing is like in the queue to, or if the node we're hitting is currently in the queue to be processed, right? So, for example, if we start with 3, 1, 2, 3, 4, right? We start at 3 marked, 3 is on the stack, so if we keep the stack over here, right? 3 is connected to 2, let's say 1 and 2, let's do 1 first. So we put the nodes on the stack in that order, right? So we say then that 2 and 1 are both on the stack to be processed, right? So now when we get to 1, we're now processing 1, right? We mark 1, we find 4, we put 4 on the stack, but we also find 2. We note that 2 has been placed on the stack for processing, right? Therefore, that constitutes a cycle. So, cycle checking using depth first search is just keeping one more array of Booleans and checking that basically every time you put a node, like every time you encounter a node, you check to see if it's already been marked in the on-stack array, and that's kind of fun because it'll give you an indication of what nodes it's forming a cycle with as well. Although not a perfect indication, there can be like other ones off branching. But yeah, so cycle detection is like the detection of a cycle is slightly different from finding the cycle. Like knowing which nodes are in the cycle and which ones are not is different from just detecting whether or not one exists, right? Yes?
So for the unstacked array, is that once marked, is that will be there or will be kind of can be removed?
Good question. So let's just continue the algorithm a bit, So we examine 4, we find nothing, so we take this off the stack, and then we uncheck on stack, right? So once we process 1, we process 4, we uncheck 1 on stack, right? Then we process 2, check, unmark that, and then we have process 3. So at the end of the day, your on-stack, like the on-stack array is always just a representation of what's in your array, or what's in your stack. In theory, you could just do something like a linear search over your stack to see if elements are in it or not. But if you keep a separate array, then you have constant lookup time, as opposed to, like if you were to do linear search on the stack, that would be a linear time algorithm that you're introducing, which is, right? It's faster to just keep the array. Cool. Question?
For cycle detection in this code array, would you not need to call the DFS on every single new edge you're adding?
You don't. Yes, you do have to do cycle checking on every single new edge you're adding. But if you use union find,
Oh no, I was wondering because last time you wrote V.
Hmm? Sorry?
Before for critical, but I assume it's cruise cycle detection.
Mm-hmm.
You wrote vertices times E plus V, so I was wondering if it could be E times E plus V instead.
So with Kruskal, the number of edges you're examining is proportional to the number of vertices, right? Because the minimum spanning tree stops when it hits b minus 1 edges. So yeah. It's been fun. I'll see you guys in the next life.
Thank you so much, Dr. Moore.